Good morning, everyone. Preparing 3D printed models for surgical simulation and planning has become a vital part of orthopedics today. We use it for complex cases such as tibial condyle fracture, acetabular fractures, calcaneal fractures, spine surgeries, and also designing patient specific jigs for our knee replacements and complex trauma cases. My name is Weber Bagaria, and I'm a hip and knee surgeon at Sir H.N. Reliance Foundation Hospital. I'm also the president and national delegate of CCOT India. So today we'll look how to acquire DICOM images, import them into a software called as HOROS. How do we define our region of interest and then export these files into STL formats? Basics about preparing G code, and then finally we'll touch upon the use of trajectories or jigs for executing complex surgeries. Once the patient has done his CT scan, the data is given either in form of a CD drive or a pen drive. They can be emailed in certain cases, and with newer cloud storage sharing mechanism like Dropbox, Google Drive, iCloud, or file exchange servers, these data can be imported into one's own laptop. This is an example of how one of the CT scan images of a patient has been sent to an email as a zipped file. The next step is to import these files into the HOROS. This is the screenshot of how HOROS look. You press on the import button on the top left hand corner, and then this dialog box open in which you can see all your files. And once you have imported these files, they'll appear as a sequential thing with certain parameters attached to these files. So you can look that this patient, Mr. Muhammad, has this CT of pelvis here, and this is when you click on his files that all the CT images on axial sections start appearing. Once we have done that, we go to the 3D viewer, again number 6 on from the starting. So 1, 2, 3, 4, 5, 6, and the seventh one is the 3D viewer format. So there is this 3D viewer tab on the top that you click, and out of this the drop down things comes. So we select what is called as 3D MIP, or the maximum intensity projection. So if you look at this image, this suggests what is the maximum intensity projection. So the second one, which is a typical radiograph, is an average intensity projection thing. And on the right side, you'll see a maximum intensity projection. And then we can volume threshold it either on a high or a low threshold. Once we do this MIP, this is the sort of picture that we get. It contains all the CT pixels that was there. So on the back, you can look at the gantry of the CT scan machine that was used. The pelvis is here. You've got a lot of tabs on the top here. You can enlarge the image. You can turn it around. You can define the region of interest. You can use the scissor tool, or you can use this what is a skull shaped tab. Now of this we use what is the scissor shaped tool, and we kind of encircle or identify the area that we don't want and delete them. So slowly we go around deleting these areas. You can see that this scissor tool is highlighted with a magnifying glass. Once we click it, this whole area goes away. Similarly, again we turn it around, see the area that we want. The skull can be used to remove a certain particular bone. This we use to remove the contralateral femur. Then again we have used the same scissor tool to remove the sacrum. And once we are happy, we go to surface rendering. Again the 3D viewer tab, and you will find on the drop down there is a surface rendering thing. You select it. Again it has got a lot of parameters in terms of the pixel values, the iterations. The standard is 300. You click on the OK. You can change the pixel values for more density or the less density. You click OK, and this is how you get a 3D image in 3-dimensional plane. Once you have done that, it's easy to export it as STL. The tab here on the settings here will show a tab called as export as STL, and you submit this or rename the file as per you want. So you can choose where you want this file to go there and you save it. It's pretty simple. Now the concept of tessellation is there. So if you look at this, this is called as a tessellation, where a lot of interconnected triangles or images are there. So this is why it is called as a standard tessellation language, so that there is no gaps remaining. So printers don't like any gap that remains. So you file format that needs to be exported is called as STL. Once that's done, you have different machine codes. We use what is called as a G code, which is sort of an address for proprietary command, and it tells the control what kind of motion is wanted. Example: rapid positioning, linear feed, circular feed, fixed cycle, and what offset will need to use. So we use G code to print the file, and this is how a 3D printer runs. You can see this is a fixed deposition model, fused deposition modeling version. It is printing an acetabulum. So beneath it are the support, and this is the extruder which is spewing out the spools, which are heated, and they kind of replicate the CT images and deposit it top by on a layer by layer fashion. So it's also called as a layered manufacturing. So on the top side you can see the ilium. At the moment the acetabulum is being printed, and their side is the E-shape. So that is how a typical 3D printer works. I call it as a jalebi maker. If those familiar with the Indian sweet jalebi, it kind of extrudes the jalebi liquid and forms a solid 3D model. Now another interesting concept is of trajectory planning, and for that we use a software called as a Blue Sky, and this is a typical trajectory planning that we'll be shortly doing for inserting a posterior to anterior screw in the acetabulum. And you see that this is a 3D printed 3D model of the acetabulum. We have chosen a screw size of 7 millimeter. We are now trying to position the screw so that it has the best fit in the anterior column. And we see that this is how we're doing it. It's adjusting 3D position for this, and we finally find that this is probably the correct position or correct trajectory that we want for this screw, so as to enable it being completely inside the anterior column. And this is how we are satisfied. And once that's done, we get our entry point and we print a negative mold so as to correspond to this entry point, so that a minimally invasive surgery can be performed. So this software is typically used by dentists, but it's got immense use in also orthopedic trajectory planning. So folks, this is about a preliminary account of how to go about making a 3D printable file from your DICOM images. It's very simplistic. There are complicated softwares like Slicer, Blender, MeshLab available, but this is something which is kind of off the shelf freeware, where you don't have to spend a lot of money and you can do it right from your computer. Thank you for your attention.